So I wanted to just kind of make this video to give you something to hold on to when you're learning about the cross product. I didn't finish everything that I wanted to talk about, so that's kind of what this video is about. And I'll try and keep it brief. So in class, what I claimed is that if I give you a vector such as the vector 1, 2, 3, and I give you another vector such as the vector 4, 5, 6. And if I were to draw those vectors, so maybe the vector A is right here and the vector B is right here, then I claim that if you take the cross product of these two, this new operation called the cross product, you do the cross product, it creates a brand new vector, call it n, the normal vector, if you will, that is orthogonal to both of these lines. So it's vectors. So it's orthogonal to the A vector, and it is, of course, orthogonal to the B vector, right? And creates right angles at both of those. And that's going to be something that is pretty important for us in the near future, aka next week. So, the formula for that we covered in class, but I'll write it down here. So to do A cross B, you set up basically a big determinant where for no reason other than this is just kind of what we do for now anyways, you stuff I hat, j hat, and k hat are little unit vectors for 3D space, our standard unit vectors there, and I would put 1, 2, 3 here and 4, 5, 6, and then we go about doing our big determinant. So there's two important things that I wanted to talk about the cross product. It's kind of seems very self-explanatory so far, like it magically creates a new vector. I'm not explaining how or why that happens. I'm just kind of giving it to us. But I want to make two comments. So the first comment is that our vectors, A and B, create, if you were to, put B up here, if I were to pick it up and move it and put B up there, and if I were to pick up A and move it right here, you might notice that the shape that we get is a parallelogram. We get a really just nice looking parallelogram right here, like so. And it turns out that that area, the area of this parallelogram, is equal to the magnitude of our vector n. So it turns out that the magnitude of A cross B is equal to the area of the parallelogram that we get, generated by A and B. Okay, so this is, for now, just a tidbit fact. If anyone's interested, like, why is that the case? Can we prove it? Yes, absolutely we can. But for now, I'm just going to say it is. And if you're interested, you're welcome to, of course, email me or ask me, and I'm happy to sit down with you and go over why it is. But so that means that, if this vector n had like a length of 10, right? If it had a length of 10, a magnitude of 10, then this region here would be 10 square feet if our units are all in feet. So if the length of n is 10 feet, then that yellow region there would be 10 square feet, which is kind of, interesting. The last thing that I didn't cover in class, which is something that probably no one really thought about, which is, this new vector n that I mentioned. I said A cross B creates a new vector n that is orthogonal. It's perpendicular to the vectors A and B. But there are two vectors that are kind of perpendicular to A and B, right? There's the vector that is pointed up, and there's the normal vector, kind of, if you will, that's pointed straight down, right? Or if you might think of this as negative n, if you will, but I'm not going to call it that. I'm just going to say that it's a different normal vector n. And you're like, well, Dylan, aren't those the same vectors? I'll say, no, they're related, but one is clearly going straight up and one's going down, and a vector has magnitude and direction, so they're clearly different. So, the more interesting question is, how do you know, visually, if you were to draw a picture, what direction the normal vector points, right? Like, how do you know that? Okay, because right now, with that in mind, which again, no one probably thought of, but do I draw it pointed up? Do I draw it pointed down? So there's two ways of thinking about this. The first way is you could calculate the normal vector, and if you're just sketching it on a 3D graph, obviously, this is going to give you some answer. It's going to have some A, B, and C component to it, and you could use that to visually draw it. But the other way that you can do it is what we call the three-finger rule, or the right-hand rule. So it's known as the three-finger rule, or the right-hand rule. And the idea is that if you're doing a cross product and you stick your first finger, right? So I'm going to say your index finger, that's your pointer finger, okay? If you stick your first finger in the direction of the first vector, so for us, I guess maybe if I were doing, let's do B cross A. If I stick my pointer finger, and you should do this literally right now as you watch this video, in the direction of this vector B, and then you stick your second finger in the direction of the vector A, your second finger being your middle finger, what direction does your thumb point? Okay, what direction does your thumb point? And in this case, your thumb is going to point straight up, right? Your thumb ends up pointing straight up, right? Like if I put my pointer finger in the direction of B, and I just naturally let my middle finger point in the direction of A, then my thumb naturally points straight down, or straight up, straight up. And vice versa, if I were to start and do the cross product of A cross B, so if we do A cross B, the only way that I can literally point my first finger in the direction of A and then point my middle finger in the direction of B would be if I turned my hand upside down so that the normal vector was pointed straight down and my thumb is pointed straight down, right? I cannot put my, just sitting here, I'm doing it literally right now. I have my first finger pointed in the direction of A, and my middle finger, if I keep it with my thumb pointed up, my middle finger points in the wrong direction. I have to literally turn my hand over 180 degrees in order to get my middle finger to point in the direction of B. And so you use the right-hand rule in order to figure out, visually, what direction the normal vector is going. Okay, so that's pretty much it. That's the only things I didn't really talk about with the cross product. So hopefully that's some interesting tidbits for you. And we will use the cross product very much so in the next week. So we'll get much more familiar with it. But this is just a little bit to kind of help fill that gap, and hopefully it helped you out.